looked at our basic functions last week, spent a couple days talking about those, and then we will be applying our transformations to like x squared, x cubed, square root, cube root, absolute value, those types of functions. The first thing on here, we need to know what the different transformations are, the different ways that our graphs can be moved, because that would save us a lot of time rather than trying to make a t-chart every single time I ask you to graph something. Okay, so if you have a function and you multiply on the outside, so if I say like 3x squared, that's my function. That 3 is a vertical stretch. It essentially just takes your ordered pairs and takes the y value times 3. Okay, so if I take, like, think about a parabola, so that's x squared. If I take all my y's times 3, what's going to happen to my graph? It's going to stretch. It's going to get tall and skinny. Think of it as if I take a rubber band, the more I pull it, the skinnier it gets, right? So we just get this tall, skinny parabola. But what if I took it times 1/2? What will that do? Compress or shrink it. It's like taking your height times 1/2. So if it's on the outside, it changes your y value and it does what it says. Multiplying by something bigger than 1 stretches it, smaller than 1 will shrink or compress it. Inside changes x, and if I'm correct, last year you did vertical stretching and shrinking, but I don't think you did any horizontal. Am I correct on that? So inside changes x, but it actually does the opposite of what you think, and that's kind of always the rule. Inside the function is our x value. If I said like 3x squared, what that's going to do is horizontally shrink my function, or horizontally compress it. Another way to think about it is 3x squared, isn't that the same thing as if I square both a 9x squared? And the 9 is a vertical stretch, and if you're stretching it vertically, it got skinnier horizontally. Okay, so if you multiply on the inside, you're multiplying by x, it's going to get skinnier. So if I multiply my x by 1/2, what do you think would happen? It'll stretch it. Okay, if I put like a 1/2 x inside my function, that would be equivalent to multiplying the y by 1/4, so it would get shorter and fatter. So inside does the opposite of what we would normally think for that reason. So bigger than 1 is a horizontal shrink, between 0 and 1 is a horizontal stretch. So what we're going to do is practice on a few functions here and see if we can kind of get a feel for this. If I asked you to graph g of x equals 2x cubed, in general, I am going to ask that you do a parent function and a final graph. The parent function is our basic functions that we were talking about last week, and when we graph those, we will do them as a dashed line. So my parent function is just, remember last week talking about x cubed? So we should all be able to get some points on that. 0 cubed is 0. 1 cubed is 1. -1 cubed, -1. You can certainly do more. My expectation is a minimum of 3. Now, is this enough to know for certain what it looks like? No, but if you knew, what does an x cubed look like? A chair. So if you know that it looks like a chair and you have 3 points, is this enough? Yes. If you don't, put in another. If you put in 2, you get out 8. -2 gives you -8. And I'm doing that dash because it's not my final answer. Everyone understand where I got that part? So this 2. The 2 is on the outside. Anything on the outside takes your y and it does what it says. You don't have to do this, but for the purpose of our example, I'm going to write out these points that I have so far. This 2 is outside my function. It's not a part of the cube. So I'm just going to take my y values times 2. Okay, if I have 0, 0, and I take that y value times 2, it's still 0. But what will the point 1, 1 become? 1, 2. Because we're changing y, and we're taking it times 2. What about negative 1, negative 1? So my final answer has 0, 0, 1, 2. I'll do that as a solid. If you don't do a dash in solid, you have to label which one is which. If you do dash in solid, I'll assume the dash was your parent function, the solid is your original. And does that do what we would expect? Think about x cubed. If you're taking the height times 2, you're stretching that rubber band, so it's going to get skinnier when we do that. Okay. What questions do you guys have? It seems like, in general, the horizontal and vertical stretching and shrinking is the hardest transformation for people. So that's why I'm writing out these ordered pairs to kind of explain it. The second one. If I said 1/2 x cubed, my parent function is the same. 0 cubed is 0, 1 cubed is 1, negative 1 cubed is negative 1. You can do more points if you like. 2 cubed is 8, negative 2 cubed is negative 8. But we have our graph.
So for the first point, it's always 0, 0?
Well, it depends on the function. I'm plugging it into x cubed. So essentially, I'm making the t-chart, I'm just not writing it down. I was just putting in some points. So 0 to the 3rd power is 0. Negative 1 to the 3rd is negative 1. 1 to the 3rd is 1. So that's where my points came from. What will my 1/2 do? It's going to take your y values times 1/2. Okay, you don't have to write out ordered pairs, but if it helps you, you can. It's outside because it's not being cubed, so all I do is take every one of those y's times 1/2. 0 times 1/2 is still 0. 1, 1 becomes 1, 1/2. Negative 1 becomes negative 1, negative 1/2. Because that 1/2 is taking your height times 1/2. If you cut your height down, you're shrinking this, so it's going to get shorter and fatter. Do you guys see how I got those points? Look at another. My function is the square root of x. So, we have to start by graphing that. Okay, if you need to make yourself a t-chart, you can. If you can talk through it, that's okay as well. If I put in a 0, what is the square root of 0? So 0, 0 is a point. If I put in 1, what's the square root of 1? Okay, 2, 3 aren't nice, but if I put in 4, the square root of 4 is 2. Can I put in negatives? No. So it looks like that. Okay. So, if I said the square root of 3x, could you make a t-chart and graph that? Sure, you'll have to strategically pick points, but let's think about our transformations. These were the points we just graphed. 0, 0, 1, 1, 4, 2. The 3 is under the radical. Anything inside changes my x values. Inside does the opposite of what it says. Okay, so this says times 3. What's the opposite of multiplying by 3? So I'm going to go through, and on each of these ordered pairs, I am dividing my x by 3. My y won't change, just divide x by 3. So 0 divided by 3 is still 0. 1 divided by 3 is 1/3. 4 divided by 3 is 4/3. So my points are 0, 0, 1/3, 1, 4/3, 2. I'm not the only one that heard you. I heard you too. Okay.
Here.
Sure, it was important. All right. So inside is my x. It does the opposite. So multiplying x by 3 is really like a horizontal compression. I'm taking that and I'm squeezing it in, which causes it to get taller when I do that. The general shape doesn't change when you do the transformation. It's just those points that are altered. So, if I asked you to do the square root of 1/3 x, would it bother you guys if I just did it on the same graph? Nobody's yelling, so I guess I will. So, it's taking my original ordered pairs, because we're basing everything off the parent function, and I'm changing my x. Now if I multiply by 1/3, inside changes x but it does the opposite. What is the opposite of multiplying by 1/3? Dividing by 1/3 or multiplying by 3. So we go 0, 0, 3, 1, 12, 2. And so we see that 1/3 horizontally stretched our graph. We took it, stretched it out, so it's getting flatter as we do that. Okay. Questions so far? I want you guys to try, just do A and B on this one. I want the parent function. So a parent function, that's your function from last week, x squared. If you need to on those, you can make a t-chart. 0 squared is 0, 1 squared is 1, -1 squared is 1. As we do more of them, hopefully we're getting to the point where we recognize when I see x squared, I'm looking for a parabola. If you weren't sure, you could always do more points. If you put in 2, 2 squared is 4, -2 squared is 4. So that's our parent. Then we look at the 1/3. Anything on the outside is changing y, and it does what it says. So I say that's on the outside because I'm not squaring the 1/3. It's not in parentheses there. So you could, if you need to, write out your points. Totally optional. Outside is y, does what it says. So if I take all these y's times 1/3, the points on my final graph are 0, 0, 1, 1/3, negative 1, 1/3. Plot those. You are getting this fat parabola here. Alright. The second one, parent function is the same. It's still x squared. So 0 squared is 0. 1 squared is 1. Negative 1 squared is 1. This time the 4 is inside my parentheses. Inside changes x and it does the opposite. Outside is y, does what it says. Inside x does the opposite. So what am I doing to my x values? Dividing by 4. So 0 divided by 4 is still 0. 1/4, 1. Negative 1/4, 1. And these two graphs end up looking pretty similar, don't they? Vertically shrinking and horizontal stretching look very similar. You do have to have at least 3 points on both the original and the parent function. Let's try C together. Okay, I have not done an absolute value today. We did them last week. Do you remember what it looks like? A V. Absolute value of 0 is 0. Absolute value of 1 is 1. 1, 2, 2. If you put in a negative, you get out a positive. Negative 1, 1. Negative 2, 2. So we just get this V. I'm writing out the points not because I expect you to, but I do think it's helping some people. So if you don't need it, that's okay. But if you do, take this time. You only have to do a few points, okay? Is this 0.25 going to change my x or my y? X, because it's inside my absolute value. Inside does the opposite. So the opposite of multiplying by 0.25, divided. So 0 divided by 0.25 is still 0. 1 divided by 0.25 is 4. Negative 1 divided by 0.25 is negative 4. 0, 0. 4, 1. Negative 4, 1. Questions on our stretching and shrinking?
Are you always dividing by number at top?
If it's inside, inside changes x, and it does the opposite. So if it's multiplying, you divide. Outside changes the y value, and it does what it says. So if it says you're multiplying by 4 on the outside, you multiply by 4. Inside is the opposite.
So like inside, you mean like inside parentheses or something?
Inside the parentheses or the absolute value or under the radical.
So since the 0.25 is being multiplied, you divide it.
Since it's inside the absolute value. Inside says do the opposite. Alright. Let's talk about this. The next thing thing that I want to discuss is reflecting. So our transformations, we can stretch and shrink. We can reflect if you have negatives. If there's a negative on the outside is y. It's saying you take your y value and you change the sign. So that will flip it over the x-axis. Inside is x. So it's saying you take your x's and you change their sign, which will flip it over to y. If you add or subtract on the end, it's outside my function. Outside is y and it does what it says. So if you add to the y, you go up. Subtract from your y, you go down. Inside changes x, so x is left and right, and it does the opposite, because inside is always the opposite. So if you add to your x, it will actually move it to the left. And if you subtract from your x, it will move it to the right. Okay, those are transformations that you did see last year. Hopefully they're a little bit familiar. So let's practice using these transformations. On most problems, I'm going to ask you to tell me, describe the transformation, graph the parent function, and the final graph. My parent function here is x squared. What does x squared look like? Parabola. 0 squared is 0. 1 squared is 1. Negative 1 squared is 1. If you wanted, you could do 2, 4, and negative 2, 4. Okay. What will this negative do? Flip or reflect over the x-axis. Okay, it's like a mirror image. If you prefer though, you can still use that strategy we were talking about with the ordered pairs. Okay, at least while you're getting used to it. Negative outside changes y, it's just changing those signs. So we still have 0, 0. Negative 1, negative 1. 1, negative 1. If you want, you could do 2, negative 4, negative 2, negative 4. We just get this upside down parabola. So what it did, took my ordered pairs, just changed the y. Outside changes y, does what it says. The second one, what does a square root graph look like? A square root? Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. If you wanted, square root of 9 is 3. You can't do negatives. What will a negative under the square root do? All it's doing, inside changes x. It's taking those points and putting a negative in front of all your x values. So you still get 0, 0, but now it's negative 1, 1. Negative 4, 2. Negative 9, 3. You're right, we can't. So here's why it's allowed. This original function has a negative in there. So if you put in a negative 4, the opposite of a negative makes it positive 4, two negatives cancel. Other questions? Okay. I am going to jump around a little bit. We'll come back and hit the ones I'm skipping tomorrow. I want to go to this slide. My parent function is what? X cubed. So what's x cubed look like? Chair. 0 cubed is 0. 1 cubed is 1. If you wanted, 2 cubed is 8. Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. What will a plus 4 on the end? Outside is y. Y does what it says. So what will happen? Up 4. So it's taking each point I just plotted and moving them up 4. If you like writing out your quarter pairs, it's just taking each of your y values and adding 4 to them. Doesn't change, still looks like a chair. It's just been slid upwards. So if you need to write out points, outside is y, does what it says. Changes your y by adding 4. If you're comfortable with it, just take your graph and move each one up 4. Last one for today. Absolute value, what's that look like? V. Absolute value of 0 is 0. 1, 1, 2, 2. Negative 1, 1, negative 2, 2. What will that minus 2 do to my graph? So I'm taking each point that I just plotted and moving it down 2. Or if you prefer, think of it as writing out your order pairs and subtracting 2 from all the y values. Any questions right now? So obviously I have a lot more examples here that we haven't covered yet. Okay, we've talked about moving left to right, but we haven't actually graphed one. We also haven't graphed any with multiple transformations, so we will do that tomorrow. I'm going to go ahead and give you a handout, but we aren't through this section. It's not due yet, so it will be due on Wednesday. So tomorrow I will finish up the notes, and then once I'm done with the notes, you will have some more class time tomorrow than you do today. But I will go ahead and give you this handout if you would like it to get started.